All right. Chebyshev, I can't say that right, but something like that. Chebyshev's theorem and the empirical rule. It says a major cab company in Chicago has computed its mean fare from O'Hare Airport to Drake Hotel to be $26.26. Based on this information, complete the following statements about the distribution of the company's fares from O'Hare Airport to the Drake Airport. Well, some crazy old guy named Chebyshev figured out that the percentage of people away from the standard deviation could be found by doing 1 minus 1 over k squared. The k is the standard deviation. So, if I am looking for it within 2.5 standard deviations of the mean, I'm going to stick 2.5 in for my k. And I'm going to calculate 1 minus 1 over 2.5 squared.
Is it going to be a decimal?
It is going to be a decimal, yes, because it's a percent.
Is it 0.84?
It is 0.84. Everybody getting 0.84 when they type that in? Yes, no, maybe? Which means if I change that to a percent then, 84%. According to Chebyshev's theorem, at least 84% of the fares lie within 2.5 standard deviations of the mean. The empirical rule thinks we have a bell-shaped curve. A bell-shaped curve just basically means everything's in the middle with something sort of like that. And according to the empirical rule, 68% lie within 1 standard deviation, 95% lies within 2 standard deviations, and 99.7% would lie between 3 standard deviations. It's always going to be those numbers. So it says, suppose that the distribution is bell-shaped if approximately 99.7% of the fares lie between this number and this number, $11.35 and $41.17, then the approximate value of the standard deviation for this distribution, according to the empirical rule, is what? What we're going to do first of all is figure out the spread between those two numbers. So we're going to subtract from 4117 to 1135 is how far? 29.82. Now since I'm finding it from the middle, what happens is the 29.82 is this whole distance. We end up dividing it by 2 because when they talk about the standard deviation, they're talking about for each side of the middle. So I'm going to divide that by 2 and I'm going to get 14.91. Okay. Now, since this says that 99.7% lie in that range, it means that we are 3 standard deviations. So we're going to take that value then and divide it by 3 because we're within 3 standard deviations. If we divide that by 3, then we get 4.97. So, according to the empirical rule, this 1 standard deviation would be 4.97.
Long day.
He's worked hard today. All right. So So, students at a major university are complaining of a serious housing crunch. Many of the university students, they complain, have to commute too far to school because there's not enough housing near campus. The university official responds with the following information. The mean distance commuted to school by students is 14.2 miles. The standard deviation of the distance commuted is 3.6 miles. Assuming that university officials' information is correct, complete the following statements about the distribution of commute distances for the students at this university. So, again, according to Chebyshev, at least what percent of the commute distance lie between 7.0 and 21.4 standard deviations? So, again, what we're going to do here, first of all, is figure out, well, what's the spread between those two numbers? 21.4 minus 7 would give me
14.4.
14.4. Now 14.4 is the spread all the way across. We want to look at a standard deviation, so we're going to end up dividing that by 2. 7.2. It tells us here, this we got 7.2. Our standard deviation, one standard deviation is 3.6, which tells me that this is actually 2 standard deviations from the middle. Now, we're still not done with that first part, because now we have to throw that into the formula. The formula said we had 1 minus 1 over k squared. The k is the number of standard deviations. So 1 minus 1 over 2 squared.
0.75.
0.75, which then is 75%. The next one says, according to Chebyshev's theorem, at least 36% of the commute distances lie between how many miles and how many miles. Round your answer to 1 decimal place. So what they're telling us there is if I do 1 minus 1 over k squared, I'm going to end up with 36%, which is 0.36, right? So I have to solve this crazy looking thing for k so I can figure out how many standard deviations away from the middle I am. So if I want to solve this for k, first thing I might want to do is what?
Times it by,
I would
actually,
times it by,
times it by 1?
no?
Or
If I want to get rid of that fraction,
2?
what's in the bottom of my fraction? The k squared.
Yeah.
So I'm going to multiply by k squared because I want to get rid of that fraction besides my variables in the denominator. So I'm going to have k squared minus, this is going to cancel, so 1 equals 0.36 k squared. I want to solve that for k. So now what should I do?
Maybe subtract the k squared.
Exactly. Subtract the 1k squared. So negative 1 is going to equal
Is it, I don't know.
0.36 minus 1. I don't think so.
Negative 0.64.
I like that. Negative 0.64 k squared. Then I end up having to
Divide by negative 0.64.
Yep. See, we got to know algebra here. So we have, I'm going to just make it positive since we have a negative over a negative.
Yeah.
We have 1 over 0.64 equals k squared. So if we want to solve that for k, we're then going to take the square root, right? So we have to figure out what is the square root of 1 over 0.64?
1.25.
1.25. Whew, we're not done quite yet. But what that tells me is I'm within 1.25 standard deviations of the middle. Okay? My standard deviation was 3.6. If I'm going to be within 1.25 standard deviations, I'm going to take that 3.6 times 1.25.
4.5.
4.5. 4.5 then is going to be my standard deviation. My middle or my mean is going to be at 14.2, so I want to be 4.5 on each side of that. So my bigger number is going to be the 14.2 plus my 4.5. My smaller number would be my 14.2 minus my 4.5. So if I figure that out, I am going to be between
9.7 and 18.7.
exactly 9.7 and 18.7 would be the two numbers that I'm between. The next part's going to be a little bit better because we're to the empirical rule. The empirical rule, if I have 68% of my population lies between how many miles and how many miles, 68% lie between how many standard deviations according to the empirical rule. We wrote it down on the previous problem. How many standard deviations am I between if I have 68% of them? Look at your previous problem. Just one, right? We said that one standard deviation was 68%, two standard deviations 95%, and three standard deviations was 97 or 99.7%. So, if I know it lies between 68%, I know it has to be one standard deviation. The problem told me that one standard deviation was 3.6, right? It's kind of like the end part of here where I knew it was 1.25 standard deviations. This one, it's just one, so it's 3.6. So it's within 3.6 of the middle, which was the 14.2. So that means I'm going to have 14.2 plus my 3.6 and 14.2 minus my 3.6.
And 17.8.
10.6 and 17.8 would be my miles then. There's my numbers again for my empirical rule. 68% lie within one standard deviation, 95% lie within two standard deviations, and 99.7% lie between three standard deviations. Part D of that. Suppose that the distribution is bell-shaped. That means we're using the empirical rule. Approximately what percent of my commute distance lie between 7 and 21.4 miles? So this is like the last one on the previous problem. First thing I'm going to do is figure out my spread of my numbers. If I'm between these two things, 21.4 minus 7 would give me 14.4. 14.4 is my entire distance. I have to go from the middle, so I'm going to split that in half, and I would get
7.2.
7.2. 7.2 is how many standard deviations away? 2. Since one standard deviation is 3.6, if I divide that by 3.6, I get 2 standard deviations. According to the empirical rule, what percent lie within 2 standard deviations? 95, right? 95% will lie within my 2 standard deviations. You can follow all my scribbling. All right. There is some evidence that in the years from 1981 to 1985, a simple name change resulted in a short-term increase in the price of a certain business firm's stock relative to the prices of similar stocks. Suppose that to test the profitability of name changes in the most recent market, the past 5 years, we analyze the stock prices of a large sample of a corporation shortly after they change their names. We find the mean relative increase to be about 0.89% with a standard deviation of 0.19%. Suppose that this mean and standard deviation apply to the population of all companies that change names during the past 5 years. Complete the following statements about the distribution of relative increases in stock price for all companies that change name during the past 5 years. So again, Chebyshev, who told me this? Oh, I think it was Jennifer in the business office. Her statistics teacher called it the Chevy Chase one because he didn't want to say that name. It's the Chevy Chase theorem. According to Chebyshev's theorem, at least what percent of the relative increase in stock prices lie between 0.51% and 0.127%? So again, first thing we're going to do is just figure out the spread between those two numbers. 1.27 minus 0.51 is 0.76, you said? 0.76. That's the entire distance. We just want to know halfway. So if I divide that by 2, we get 0.38. 0.38 is how many standard deviations? We know that one standard deviation is 0.19. If we have 0.38, we get 2 standard deviations. Now in order to find the percentage, we have to throw it into our formula. We already did this one. Right? 1 over 1 minus 2 squared gave us what percent?
75.
Yep, it was 0.75, which is 75%. If I remember right, the drop-down is going to have like 4 choices, so hopefully you get close enough to get the right one. They won't be really close together. The second part of that, according to Chebyshev's theory, at least what percent of the relative increase in stock prices lie between 0.605 and 1.175%. So part B, pretty much just like part A was on that one, right? We're going to start by finding the spread. 1.175 minus 0.605. 0.57. We're going to divide it by 2.
0.285.
0.285. We have to figure out how many standard deviations 0.285 is. So since one standard deviation is 0.19, if we take our 0.285 and divide it by 0.19, we get how many standard deviations?
1.5.
1.5. Once we know how many standard deviations, we can throw it into our formula. 1 minus 1 over 1.5 squared then.
0.5.
Round to the nearest. Does it tell us to round to the nearest? did I write my mess? Rounded off, oh, round to, okay. It's a drop down. It actually rounded it off to the nearest whole number.
So 1.
So what did you get when you did this one?
It's 0.5555555.
So they rounded it off to 56% is what the choice was in the drop down. It's 56%. Part C. I like the empirical rule better than the other one. Suppose that the distribution is bell-shaped. So according to the empirical rule, approximately what percent of the relative increase in stock prices lie between the 0.51 and the 1.27? So we already figured that out. If I did 1.27 minus 0.51, we had 0.76. We divided that by 2, which was 0.38. 0.38 was how many standard deviations? So we divided that by the 0.19, which was 2. Okay, we should have the same number of standard deviations here as we did there because we had the same numbers, right? So according to the empirical rule, what percent lie within 2 standard deviations? 95. That was from our little table that I wrote down a few times. 68% lie within 1, 95% within 2, 99.7% within 3. And the last one on that one. Suppose that the distribution is bell-shaped. According to the empirical rule, approximately 68% of the relative increases in stock price lie between what and what? 68% is how many standard deviations according to the empirical rule? 1 standard deviation. 1 standard deviation was how far? 0.19. So we want to be 0.19 from the middle, which was 0.89. So we're going to do 0.89 plus or 0.19 and minus it.
Be 0.7 and 1.08.
So we're going to be between 0.7% and 1.08%. So if you haven't read chapter 3, when you read that, this will make a little more sense maybe.